basic things that we are covering here about our material science. So when you are reading, when you are getting know about our atomic structures, basically about the chemistry, right? This is regarding the chemistry, and most of you know each and every element is consist from atoms. Right? Most of the time we are having atoms. So in an atom you have electrons, protons, and neutrons. So history behind this atomic arrangement is, in every part of a kind of that means innovation, we have to have identification of what is behind that. So there are so many researchers that find about what is called this atom, right? So in that kind of, we have to identify what is the historical perspective of finding an atom. So there are some philosophers, right? They have given their ideas as a philosophy. So that is called theories. I think all of you heard about that. So in the historical background, you have atomic spectra as a kind of a concept, and again quantum theory. Now you know about quantum mechanics, quantum physics. So these things are behind the quantum theory, and again the atomic structure. So you heard about Dalton, right? And again Faraday, Rutherford, Bohr, right? Planck, Einstein, right? Those are kind of huge legends when you are considering this atomic history. So after that, this is the atomic spectra, quantum theory, and atomic structure. So they have identified something behind that, but they can't actually prove it because they do not have kind of a technology now we are in. Right? We have so many technologies now, so many software, so many theoretical things, and again some practical things that you can show it as like Zoom, right? But at that stage there is no any kind of technology that you can prove it. So they have developed their philosophies using something called theories only. So Dalton have some atomic nature theories. Faraday have electricity and magnetic theories. Right? Thomson is developing electronic, that means EMF. And again, Robert Millikan, you have oil drop theories. Rutherford, Goldfoil, nucleus theories. And Bunsen, first spectroscope, first live spectrum is developing. Then Locklear, likewise, you have a kind of a historical background there. After that, now we are developing our kind of structures. Again, the Bose module, right? Bose scale you I think heard about. So developing from Bose to Einstein, Planck theory, all of are becoming like quantum theories. So most of them have kind of a basic background through this electromagnetic radiation, because they studied about materials. So most of them have kind of a basic background through this electromagnetic radiation, because they studied about materials using this electromagnetic radiation, right? They use some kind of rays which directly hit on this material, and there is a reflection from that. They studied that reflection and identify what is going on and what is behind that. That is called nature of light. All of you heard about it, right? Nature of light, how it changes, right? So you know light is a wave, right? Wave means you have a kind of frequency, right? And you have a lambda value, that means the length of wave. And after kind of changing of wavelengths or the frequencies, that means your material is going to be changed, right? Then they study about this wave, the nature of wave, what is a wave and what is waving, after knowing about this rays and light. So this is a wave. And I know that you are already aware of this one. Waves, they have a wavelength and amplitude. This lambda is a wavelength. You know, that is one of a unique identification for a wave, that is lambda. And again, the amplitude, it is capital A. So wave is some sort of a periodic function. You can see that periodic means this shape is happen some kind of a time gap, right? It is what we call lambda. So after a lambda, you have another kind of same one happens. So that is called periodic function. So something that periodically change versus time, that is called wave. Then wavelength, the distance between equivalent points. Equivalent points means this is an equivalent point. That is the maximum point that you can reach as a wave. So this is the starting point of a wave. So if you get from here to here, that is also called wavelength, lambda. Then amplitude, that is the height of wave, maximum displacement of periodic function. So that means this material goes to here, that is the maximum distance that a material can change, that distance. That is called amplitude. These are some kind of properties behind the waves. You have a higher frequency wave, right? So if you have a higher frequency, then the wavelength is getting shorter. Then if you have a lower frequency, that means longer wavelength. Wavelength means lambda. Here you can see the difference. So the number of waves passing a given point per unit time, it is called frequency, right? For waves traveling at the same velocity, the longer the wavelength, the smaller the frequency, right? This one. So this is a kind of higher frequency. That means it change less time. Right? This one can't change. That means it consume more time to change, right? That is the higher frequency and lower frequency. Wavelength lambda, complete cycle. That means this one is repeating here, right? So this shape is repeating here and the wavelength is not changed. Then wavelength, half of that in A. Now you are reducing your wavelength into half of this one. Then frequency twice. And if you reduce the wavelength, then your frequency is increasing. But the amplitude is same. Again, same frequency but smaller amplitude. You can reduce the amplitude. So amplitude actually means about the energy of the wave. So different aspects of having those wavelengths and amplitudes, right? And again, this is a light wave. You know that we have three-dimensional materials, right? Three dimension, you have X, Y and Z. So according to X, Y and Z, you have light going. You know that we have three-dimensional materials, right? Three dimension, you have X, Y and Z. So according to X, Y and Z, you have light waves which is going along X-axis, going along Y-axis and again Z-axis, right? So that is a light wave that you can use. You have a parallelly electric field and a magnetic field, right? The Faraday is the one who find it and Maxwell is going to be proving. And again, you have a electromagnetic radiation. I think all of you know when your frequency is getting changed, right? That means your F change, then you have a wave change. Here you have gamma rays, X-rays, ultraviolet, then visible light, infrared, microwaves, and radio frequency. That is the what is called electromagnetic radiation spectrum. Right? So in that spectrum, in the middle point, you have a visible light radiation. That nanometer is changed from 400 to 700 feet. So I am just mentioning about these basics. I know that all of you are aware of that, but this is a recap of your past memories, right? And again, this is a speed of light in other sort of materials. We call induction of refraction, right? That is C over V. So here are some materials. In a material, the vacuum is get 1, right? That is very same as what you are developing in a material. Here you have glass, salt, asphalt, diamond, lead. So from this table you can see the light which through the material is going to be changed, right? That is what it means. The frequency is going to be changed due to the change of the material. That means the kind of a property behind the material. If the properties are changed, then this one is going to be changed. That is what they are actually that what they were looking at, right? They are investigating about this one. What happens to the light when it goes through this material, right? Then after kind of a research using these light waves, they actually develop these theories, right? So now we are going to start our session about atomic structure, right? That is the history behind that. So after that they develop this structure we call atomic structure. So that an atom consists of a positively charged nucleus. That means inside an atom you have electrons, protons and neutrons. So in that neutron is we call neutral, that we do not have any charge, but electron is negative here and the proton is positive and neutron is not charged. So inside nuclei you have only neutrons and protons. So protons are positively charged, electrons are negatively charged. But if you get an atom, right, it is called neutralized atom, right? So neutralized atom means you have same proton and same electrons. Because if you have positive and negatives are equal, then we call it neutral. So the nucleus contains protons which are positively charged particles and neutrons which are neutral particles, right? The electric charge, so please mention this one, that is the charge of an electron, we call coulombs, 1.6 into 10 to the power minus 19 coulomb, right? So we are measuring charge using coulombs, right? Capital C. Carried by each electron is equal to the charge carried by each proton, right? So the values are equal. That means positive value and the negative value is equal. If you get a proton, that value of coulomb is equal, but the sign is changed. Electron is negative, proton is positive. So therefore, in a neutral atom, the number of electrons is equal to the number of protons. Right, now we have a kind of a background. Inside a material you have atoms, and inside atoms you have this here, He, right? This is the element symbol that we can represent. And now we have two different kind of notations here. At the top one we name as mass number. At the bottom one we call it atomic number. And if you find this type of arrangement, this atomic number is relatively described about the number of protons inside the element, right? So if you have mass number, that means total protons and neutrons inside the nucleus, right? That is how we notify this one. So please keep it in your memory. If you have a notation like this, right, if you get helium, then you have atomic number is 2. That means you have 2 protons inside your nucleus, right? That means positive number is 2. That is the atomic number. But if you get mass number, now it represent 4. That means you have proton plus neutrons. Inside nucleus is 4. I think now you can calculate how many neutrons inside helium nucleus. Only thing is you need to divide 4 by reduce 4 by 2, then you get 2 neutrons inside helium nucleus. So that is the importance of this notation. And again, if you have this atomic number, then you can find how many electrons in a helium atom. Because you know, if the helium atom is neutral, then your positive and the negative are equal. Then if you have 2 protons and your helium is neutral one, then suddenly you can see electron is equal to this one. Then you have helium atom is consists of 2 protons, 2 electrons, and again 2 neutrons. That is most important one to identify, because if you have this kind of notation, you have to identify what are the properties behind this one. Okay, now this is the helium atom. So if this one converts to helium 2 plus ion, right, I think you know this one. If this one is going to be how many electrons are there and how many protons are there and how many neutrons are there. So helium 2 plus means, right, you are removing 2 electrons, because 2 positive means you are having 2 more than positives inside your atom. So that means you are removing 2 electrons. Okay, if you have helium 2 plus ion, then that includes, here you have 2 protons, right, in a helium atom. Now you have 2 electrons, but what happens, you removing 2 electrons means you remove total electrons. The number of protons or electrons in an atom is known as atomic number, but you have to remember, it is most important thing is you need to identify that is a protons, right? Because if you have ions, you can't just say that is equal to the atomic number. So element, the material that is made up of atoms having the same atomic number is called an element, right? That is what we identify, helium. Then isotopes, atoms of a particular element having the same number of protons but different atomic mass are called isotopes, right? So identify that one. The only change is the number of neutrons are changed, right? That means your mass number is getting changed. As example, if you get helium, right, in the previous case here, helium you have 2 and 4 here. But if you are having another one called 2 and 3, right, helium 2 and 3, the 2 is the atomic number, 3 is the mass number. So if you have this type of 2 different types, it is called isotope, right? So in the helium 2,4, now you know what are inside. If you have 2,3 helium, right, if it is 3, then you can see protons are 2 and neutrons are reduced to 1, but same element, same helium, but you have different mass number. So that is called isotopes. Then atomic mass, we call atomic mass number. The total number of protons and neutrons inside the nucleus is turned into atomic mass or atomic mass number. It is expressed in atomic mass unit AMU, right? So normally we didn't call it AMU, but some data sheets also they arrange AMU. So AMU means it is a kind of a mass multiplication. So this is the mass of a proton, right? Then you can multiply to find atomic mass number, right? If you have 2 protons, 3 protons, that is how we can multiply by this one, right? So here, this chart you can see the characteristic of these particles. Proton, you have charge of positive 1.602 into 10 to the power minus 19. Mass of proton is 1.6726 into 10 to the power minus 27 kilograms. Neutron, you didn't have any charge. Then the same as proton. Then electron is negatively charged, same as proton, and the mass is 9.1095 into 10 to the power minus 31. Right? That is the mass and the charge of our particle inside the nucleus, inside the atom. Then electrons in atoms. Now I discussed about the models or concept, right, in the previous one. I think if you want to conclude on Bohr's model, right, that is Bohr's model. Now we need to discuss about the Bohr's model. Right? So he described the negatively charged electrons are held to the positively charged nucleus by an electrostatic force of attraction. So Bohr proposed a model of atomic structure in which electrons move in fixed orbits. Right? We'll discuss this one. Orbit shells round the nucleus, and they are stable in these orbits. That is what he expressed, because he didn't have anything to prove this one. Only thing is he expressed in words, right? He expressed in ideas and doing some sketches, right? So in early stages we only find some of sketches what they have developed. So electrons in orbits close to the nucleus have strong force of attraction holding them in orbit than electrons which are in orbits. I think you know that nucleus can't move, but the electrons are moving around the nucleus. That is what he says. So thus each orbital electron possesses a specific amount of energy. Each orbit represents a fixed energy level for an electron. Right? We'll discuss what is going inside this one. The ground state is defined as the energy situation being existing when electrons are not excited. It represents the lowest energy state of the atom. An electron can only emit or absorb energy when making a transition from one orbit to another. Right? We discuss. To jump between energy levels, an electron must collect or emit exactly the right amount of energy. So when an electron is excited by an input of right amount of energy, it moves to an orbit of greater radius when an electron moves back. Right? That is what he modeled, because he already did some sketches and he expressed these words. Right now we have to identify them. Again, after Bohr's model, we call quantum model. Right? In Bohr atomic model, it is stated that electrons are revolving fixed orbit, and these orbits are described by quantum numbers. Right? That orbit is called quantum number. So these numbers are required to define complete the energy state of an electron in a given atom, and there are 4 quantum numbers. So that is very important. When a Bohr model about fixed orbits is converting into quantum numbers. So there are 4 different quantum numbers. We call principal quantum number, notification is simple N, orbital quantum number, that is simple L, magnetic Mi, spin Ms. Okay, we will describe this. The 4 quantum numbers must be defined to fix the energy level of an electron. Right? So we know you have so many electrons inside the atom, then we have to understand how they are changing and how they are developing. The orbital quantum number determines the shape of subshell. Right? Then the magnetic quantum number describes the magnetic moment of an electron, while the spin quantum number describes the spinning of electron in either clockwise or anti-clockwise. Right? So this is just about a summary. Okay, quantum numbers. So solving the wave equation, we have waves from the light. You know what is a wave equation means? V equals F lambda. So finding a wave using wave equation, and they use that wave, that means the light, into the kind of a material, right? right? They hit this light into a material and investigate what is behind that, right? Now they have developed these wave equations and after wave equations and find what is the difference in between after and before. Finding out about the changes, they develop these orbital models, right? So each orbital describes a spatial distribution of electron density, and orbital is described by a set of 3 quantum numbers we call integers. Okay, we'll see what is this 3, right? We have 3 dimensions. So need 3 quantum numbers to define a given waveform because we have 3 dimensions. You need to have a x direction and you need to have a y direction and z direction. So another name for wave function is called orbital. So describe they have orbitals. The orbitals are defined from wave functions. There is 3 dimensions. Okay, then they develop principal quantum number n, right? The principal quantum number n describe the energy level on which the orbital resides, right? That is what orbit is consists. So largest E difference is between energy levels, right? We call energy levels. The value of n are integers. Integers means 0, 1, 2, 3 into n. That is how a quantum number defines. Then orbital quantum number simple. L define the shape of the orbital. We need to identify what is the shape of the path that electron moves. Because it may be round shape or oval shape or square shape, right? That shape is called the orbital quantum number. So that allowed value f integers from 0 to n. Here what it means 1 to n because it is an integer, but now here we use 0 to n for the quantum orbital number. So we use letters designations to communicate the different values of L and therefore the shapes and the type of orbitals. Right here you can see, I think you know these things, S, P, D, F. Those are the orbitals. We have S orbital, P orbital, D orbital and F orbitals. Right. So each of these have different kind of shape of their orbitals. Right. So orbital numbers start from 0, then it goes to n minus 1. Because you have quantum number, that principal quantum number 1 to n, then you need to have orbital quantum number 0 to n minus 1. Right? That is how it changes. Then magnetic quantum number MI describe the t-dimensional orientation of the orbital. Right? Values are integers, but it ranges from minus L to plus L. Minus L means this one, right? It changes minus L to plus L. So therefore, on any given energy level, there can be up to 1s. We will discuss. This is kind of a summary. And 3p, 3, 5d, 7f like this. So many orbitals are there. Here you can see 1s, 2s, 2p. Likewise, it goes to higher energy levels. That is called magnetic quantum number. Right? Here, if you have principal number n equals 1, then possible L values, you know n minus 1. So if it is 1, then it goes to 0. Then subcell designation is 1s, right? Because you have SPDF subcells. Then possible value of Mi is 0, right? The number of orbitals in subcell is 1. The total number is 1. If you move to second one, you have 2 possibilities, that is 0 and 1, right? 0 and 1 means you have 2s and 2p. So no need to worry about this. We will discuss using the diagrams, right? Then possible values 0, 1, 0 and minus 1, right? Is minus L to plus L. Right? L equals here 1. Then you move to 1 to minus 1. Again, you have 3 different type of subshells. So total is 4. Likewise, you can divide this one. So after describing these diagrams, you can easily identify. Right, and this is the orbitals and nodes. Orbital S is a symmetric of spherical shape, right? That is a quantum one. Then node geometry is spherical, and the node is n minus 1, and the orbitals is 1, right? Because here you can see only S is having 1, but P is having 3, right? You can identify those things in the diagram. Then P is cylindrical shape, D again a complex shape, and F is also a complex shape, right? Now you can identify the S orbitals. Here this is the shape of a S orbital, right? S orbital means orbital quantum number. The value is 0 because L start from 0. Then you have different shapes. That means 1s is this much, then 2s is this much, then 3s is this much. Because if the size are increasing, that means you have the number of electrons are increasing. That is why this spherical shape is increasing, right? 1s is lower, then 2s is higher than that, 3s is somewhat higher than that, right? That is due to the number of electrons inside the orbital. Right here you can see the shape and what is the energy levels, energy gaps. And this is the p orbital, right? Because these numbers are, this is this notification, that means the letters N, P, S, like D, F, those are coming from these alphabetical orders that they have developed, right? So only thing we need to identify these notifications. Then P orbital is value, L is 1, right? You know that. Then have two lobes like this, because you have P orbital, you have L equals 1. So L equals 1 means here you have 3 subsets, right? So 3 subset means you need to have different 3 angles. So now you have x1, y and z, 3-dimensional, because you have 3 orbitals, right? So that is how the p orbital exists. Then D, you have 4 different types, right? Likewise, you need to have 4 different, and again this is the 5th, right? This is just a value is 2, then 2 nodal planes, because 2 means -2, -1, 0, +1 and +2. So different 5 arrangements. That is why this becomes 5. So 4 of the 5 orbitals have 4 lobes. This one. The other resemble as p orbital with a donut around the center, like this one. That is how they define these orbital shapes, right? So only thing you have to identify, this is the shape of the orbital if it denotes d orbital, right? Then we need to identify how electrons are configured in these orbitals, right? So distribution of electrons in different shells and subshells of an atom in accordance with the Pauli's principle, because we discussed what is Pauli's means, known as electronic configuration. So electrons are added to fill up and complete one shell after another, and when shell or orbit contains 2 and 2 electrons, it is said to be complete, right? Because if you have this one, if one number, that means n is 1, and s you have the maximum number of electrons is 2, right? If you have 1s, that means you have 1s2. That is the maximum number of electrons that s orbital can exceed. Then again, if you have 2, that means you have 2s and 2p, right? So 2s have maximum of 2 numbers of electron. Then p you have 3 orbitals. So one orbit can access 2 electrons. That means means you have 6 electrons in the p orbital, then 6 plus 2 is 8. Then 3 you have 3s, 3p and 3d, then it means s means you have 2, p is you have 6, then d is 5, that means 10, then it is 18. Likewise, you can find the maximum number of electron of the principal quantum number. Right. So this is how we identify our maximum amount of electrons using the quantum numbers, principal quantum numbers. So this chart will help you to identify how the electrons are filled. Right. So electron configuration followed by orbital SPDF. Superscript above the orbital letter indicates the number of electron it consists, like this one. This is the that means orbital quantum number, and this is the principal quantum number. If n is 1, you have only one s because L is 0, right? Then it goes 1s. And if you have n2, you have 2. So this is how the electrons are filled. It goes to 1s, then becomes 2s, and now it goes to 2p. So if you have 3, 1, then it is 3s and goes to 3p and comes to 4s and goes to 3d. Likewise, those electrons are filling. Right? That is how we write our formula of the atom. This is how we write our electron filling. 1s2, 2s2, 2p6, like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, then 4p6, 5s2, 4d10, 5p6, 6s2, right? Likewise, we can 4f7, 14, 5d10, 6p6. Likewise, that is the electron filling order of an atom. A convenient memory device for this order is to list the orbital as shown below and to use a series of arrows on the orbitals as shown. By following the arrows from tail to head, the order is indicated. So likewise, you can just draw this one and you can fill this order. Right. So this is what you need to identify. Right. So total what we discussed up to now, you can just identify by this one. So these are the energies of orbitals. That means energies of orbital means so here we already identify this model of this one, right? Inside the nucleus you have protons and you have electrons around the nucleus, right? Here this is the model of that we are discussed. This is the energy level. That means if you want to fill an electron to an atom, right? This is how electrons are filling, right? So this is the energy level. If you get 1s orbital, as example, if you have hydrogen, you know hydrogen is atomic number is 1, right? So atomic number 1 means you have only s orbital, right? Because if you have atomic number 2, then you have 2 numbers of orbitals, like here, right? So just you need to identify this one. Then if you get hydrogen, we have only 1s, right? So I think you already heard about the periodic table and you know what are the elements inside the periodic table and you know the groups, horizontal and vertical, right? So in a horizontal line, you have hydrogen and helium, right? So inside the hydrogen and helium, you have only one orbital, that is s orbital, right? So 1s is the lowest energy level of an orbital, right? And after that, it increases the energy to the second energy level, that is n is 2. So in the second energy level, that means principal quantum number, you have two different orbitals, that is s orbital and p orbital, right? So s orbital you have one orbit, in the p orbital you have three orbits, z, x and y, right? Okay, so this is the energy arrangement of an atom. So if you want to fill the electrons to the energy levels, first if you feed one electron, it goes to this level, it is 1s. Then if you goes another electron, then this orbit can generate two electrons. That means it can include two electrons. So if you feed two electrons, then these two electrons can include in 1s orbital. That is why it becomes 1s2, right? So hydrogen you have 1s1, that means you have only one electron. So that electron is in this principal quantum number, it is 1s1. So if you feed another electron, that means s2 orbital. So you have s orbital and it can maximally include two electrons, then it is 1s2. Again, if you want to add another electron, then this s orbit can't include three electrons, then that extra electron has to go to this level, that is 2s1. So you have hydrogen, helium and beryllium. Then beryllium have three protons, that means it equals 3 electrons. So if you have 3 electrons, the third electron should goes to 2s1, right? This is the energy level, and 1s1, 1s2 is here, then again 2s1, 2s2 here, then 2p1, 2p2, 2p3, then 2p4, 2p5 and 2p6 is here. Likewise, electrons are filling, right? This is how it goes, 1, 2, then 3. Likewise, it comes to energy levels, right? S is the lowest energy level, then P is the second, D is third, and F is the highest energy level, likewise. So these are the shapes of our energy orbitals. This is the s orbital, this is the p, and this is d. Again, f is having 7 different angles. That is kind of a complex kind of arrangement. So up to now, if you need SPD, that is enough. And this is what they are actually looking at, we call photoelectric effect. Then they use their radiant energy, that means rays, into a surface and identify what emitted after hitting on the surface. And that is how they identify this kind of models. But if you are using the quantum mechanics, that means this kind of arrangement without proofing, here are some kind of problems are arising, right? So it's not hard to solve equation for the various of wave function if they all alone, like hydrogen. The problem is what happens in the presence of other electrons, right? How to identify how these electrons are filling, right? Then the electron interaction problem, because in an orbit you have, if s orbital you have 2 electrons, in p orbit you have 6 electrons. So they are how they interact each other. Then electron interaction so complex, then exact solutions are only possible for hydrogen. But helium you have 2. Then how these 2 yes. Those are the kind of issues that they have just arrived because they do not have anything to prove. Because now we have those softwares, now we have some kind of visualizing things, but at that stage they do not have something like softwares or like that to prove this one. So only thing is they are doing sketching. So using that sketching, they have arise these kind of questions. The electron interaction problems, the electron interaction complexity, and the electron probabilities overlap, right? So those kind of things are overlapping, and again Pauli is getting another kind of principle for this type of interactions, right? That is called Pauli's exclusion principle. He said that inside an orbital here, he said that inside an orbital here, because now we said in an orbital you have one s, only one orbital. If you move to p, you have 3. So inside p you have another 6 electrons, right? So inside this kind of an orbital there are 2 electrons. So these 2 electrons are moving against each other. That means we have 2 different directions, that is called clockwise and anti-clockwise. That is what this one notified. If one electron rotates to clockwise, then the other one rotates to anti-clockwise. Okay, we will see this video and you can identify.
Around the atomic nucleus, electrons spin on their own axes.
This is how. This is the spinning, and you can see this electron is also rotating.
Generates a magnetic field.
Right. So this is the nucleus. This is the electron, and again the electron also rotating. So you can have clockwise and anti-clockwise like this. Right. So this is kind of a arrangement inside that orbital SOP. Right. This is the Pauli's principle. He said no 2 electrons in an atom can have identical value, because for all the quantum numbers. So in other words, no more than 1 electron can occupy each energy state, which is completely defined by a set of 4 quantum numbers. So thus if 1 electron occupies one energy state, then the possibility of second electron occupy the same state is excluded. That is why it gives 2 different arrangements. Then you know, if you rotate to clockwise, there is an positive magnetic field. If it is rotates to anti-clockwise, then it is negative magnetic field. Then that is why it is positive and negative, right? So after including this principle into the quantum one, they can prove it, right? That is why he developed that. So it calls the spin quantum number. That is the 4th one I already mentioned, because you have principal quantum number, then you have orbital one, right? And again this spin quantum number, likewise I already mentioned in the previous slides, right? You have 4 different levels. As I mentioned here, right? The principal quantum number, orbital quantum number, magnetic quantum number, and spin quantum number. That is what I mentioned here. So this is the spin quantum number. So spin means you have 2 directions. That means clockwise and anti-clockwise. So those numbers are indicating what is the real atom means, right? Then spin quantum number ms is a 4th dimension required, because you know that integer is positive, but the direction is positive or negative, right? Because kind of orbital has 2 electrons, but 2 electrons cannot get the same numbers. Then that is why they separately use positive half and negative half. So if you just identify positive half electron inside s orbital and negative half electron inside s orbital. That is how these two differentiate, because if you can't differentiate these two, then same number will generate to both of them, right? So after the same number is there, then you can't differentiate what is the first, what is the second. But if you just looking at this one, if you say positive half electron inside s orbital, negative half electron inside s orbital, then you have differentiate both these two electrons. That is why this Pauli's principle is there, right? So this leads to fourth quantum number, spin quantum number SF. The spin quantum number, two values, plus half and negative half. They describe the magnetic field of vector inside electron. So this is the kind of proof that they have developed. Electron have two different arrangement, that means clockwise and anti-clockwise, right? So this is a kind of atom beam, goes to a slit and goes through a magnetic field, right? You know the left hand rule and right hand rule, Fleming's left hand rule and right hand rule. If you apply just here the left hand rule, then you get two different directions. If a positive is goes to this direction and the negative is goes to that direction, that is the spin means. Because if you do not have plus and minus, then just total goes to this middle direction, right? So after inspiring this one, because you have different two directions, that is why generates this collector, right? But their investigation is that if you have this kind of atomic beam through a magnet, then you have two different patches in the collector, so that it provides that kind of evidence. They can think about this electron arrangement inside an orbital, this one. That is why they said they have different kind of clockwise and anti-clockwise rotational electrons inside the orbit, right? Then they said why that is called spin, right? Because they said that a charge that spin produce a magnetic field. So if you have a magnetic field, means they are separating each other, right? If you have positive and negative, then you know they are interconnecting. But if you have different rotations, you know that the momentum theory you have, if it rotates clockwise, it goes to forward. If it is anti-clockwise, it goes to backward. Likewise, you have a momentum here due to the spinning. So no two electrons in the same can have exactly the same energy. That is the second principle of Pauli's. Then for example, no two electrons in the same atom can have identical set of quantum numbers. That is how they prove it. So they said if you have different arrangement, different rotations, then there is a different magnetic field. So that magnetic field can differentiate these two electrons inside an orbit. Then they develop this arrangement to show how electrons are feeding. That is the electron configuration. So electron configurations, every electron has a name. They said if you have electrons inside orbits, because as like your identity card, right? Because there is no any identity card for 10 persons, only one person having one identity card. So that is why they said if you have electrons, then they have separate identities. Then they develop this module. Name of each electron is unique. So name consists of 4 numbers: N, L, M, I, and MS. Right? As example, like your name, Mr. George Herbert Walker Bush, like, right? Your name also there, no? You have different names. So that name also we are using twice. right? So we must learn to name our electrons, because if you have 15 electrons in your atom, then just you have to have some identification. What is my first electron? What is my second electron? And what is my third electron? Likewise, you have to have a identity for your